When I first started messing around in Unity, there's one thing that really confused me. I'd open up Unity, make my first project, and somehow figure out how to place a cube into the scene, and then be like, cool. Now how do I make it move? And for some reason I could never seem to get a clear answer to that question. Now it is entirely possible that my young, naive, untrained former Unity self was simply not asking the right questions, but it seemed to me that no matter where I looked, no one had a simple answer to what I was trying to figure out. So I figured that now that I'm a certified Unity expert with 100% full knowledge of all things Unity and otherwise, I'd make a tutorial on this very subject to help any other wayward Unity souls lost in a sea of confusing information. So without further ado, here's how to make things move in Unity. So there are essentially four main ways to make things move in Unity. There are a few others, but they're a little too nuanced to be considered. The main four ways to create movement are translation, physics, the nav mesh, and animation. Now using a nav mesh or animation can be pretty advanced and get pretty complicated, so for the purpose of this video, I'm only going to talk about translation and physics. However, it is worth noting that under the hood, both the nav mesh and animation make use of translation and the physics engine. And even the physics engine makes use of translation. So let's start with that. In order to understand what translation is, we first have to go over the concept of a transform. A transform is the most basic component of any game object in Unity, and you can see this by creating an empty game object and seeing that it only contains a transform component. A transform component contains information about an object's position in space, its rotation, and its scale. This information is what gets manipulated whenever you want to move an object around in Unity or change its size. So what is translation then? Well, translation is essentially just the process of manipulating an object's transform position to make it move around in the scene. So given this knowledge, how do we actually tell Unity to move the object whenever the game is running? Well, as with most questions of that nature, we'll have to write some code. The first thing to do in order to move an object whenever the game is running is to create a script that we want to attach to the game object we plan on moving around in our game. I've created a script in my project called Movement Controller, which I plan to use for just that. After creating the controller script, the next thing we need to do is attach the script to the game object in our scene that we plan on moving. I'm going to attach the script to this cube I've already got in the scene. To do this, I'll simply click on the cube object in the hierarchy, and then click and drag my script into the component section of the cube over in the inspector. Another way to do this would be to select the cube object and click on the Add Component button in the inspector and type in the name of the script you want to attach. So now that the script is attached to our cube, let's actually open it up. You can do this by simply double-clicking on the script. Mine will open in MonoDevelop, but opening the script in Visual Studio is totally fine too. Okay, so now that we have the script open, the first thing we need to do is write some code telling Unity which game object we would like the script to affect. Now, before I go any further, I would just like to say that I'm going to be tossing around some programming terminology that I'm going to assume that you'll be able to understand in order to write all of the following code that will make our cube move. If you don't understand some of the programming terminology, or are new to programming, don't worry, because you should still be able to follow along. I may eventually make a video going over some programming basics later on, but until then, I recommend not worrying as much about all the programming lingo. Alright, so back to the code. There are a variety of ways to tell Unity which game object we would like our script to affect, but the most common way is to declare a public global variable that we want our cube to be, and then drag and drop our cube object into the newly available cube variable located on our movement script back in the editor. It is important to note that if we want the variable to appear in the editor, we have to make sure that our cube variable in our code is set to public, or that we set it as a serializable field so that Unity knows we want to be able to change it in the editor. That's one way of doing it. Another way to assign our cube variable would be to write some code in the start method telling the script to assign the variable to whatever game object is in the scene with a name of cube, or by giving our cube object a tag and telling the script to find the game object with that tag. This can be a useful way to declare variables in certain settings, especially when we want to make something dynamic at the start of our script, but it's not a good idea if we have a lot of game objects with the same name or tag and if we're worried about performance. Now we could use any of these methods to get access to our cube object, and all of them would work, but we actually don't need to do any of them, because since we already attached this script to the game object we want to move, we can actually access the object directly by calling this.gameObject in our script. Once we've done this, we can start to dive into actually writing the code that will move our cube. However, before we do that, we need to go over the concepts of vectors as well as world space and local space. Let's start with describing what a vector is. A vector can pretty much be described as a variable that serves as a list of numbers that correlate with spatial dimensions in Unity. So for instance, vectors are typically associated with an object's position in space or with directions in space that we want something to go in. So in the case of our cube, its position in space as specified in the transform component is stored in a vector 3, which is a vector containing 3 numbers which correspond to each of the 3 spatial dimensions, x, y, and z. Given this, it is possible to access or manipulate our cube's vector 3 position variables directly, and in turn, make it move. So let's give this a try. The code to move our cube like this is fairly simple. We'll start out by adding something into our movement script in our update function to register user input. The reason we put this in the update function is because this function is called every frame, so anything we put in there, such as code to register us pressing a key, is run every frame, and therefore can detect changes in our code or input in real time. The code we need to put into our update function is an if statement that only runs certain code when a certain button is pressed. In this case, I'm going to go with the spacebar. To do this, we would write if, then input.getKeyDown, and then pass in the variable keycode.space. This code means that whenever the spacebar is pressed down, the code within the if statement will run. Now we're ready to actually change the position of our cube directly. To do this, we will need to make use of the this.gameObject method I mentioned before, and also decide which axis to move on. I'm going to go ahead and move the cube on the x-axis. The code for this will go in our if statement, and will be this.gameObject.transform.position plus equal new vector 3 and then 3 variables 1, 0, 0. This code grabs a reference to our game object and its transform position and adds 1 to its x position every time we press the spacebar. The plus equal is just shorthand for setting the cube's position equal to its current position plus the new vector 3. And the reason we add a vector 3 to the position is because we can't change specific numbers of the position of our cube directly. We have to change the position vector as a whole. So now if we go test this back in Unity and hit play, we'll see that our cube now moves on the x-axis every time I hit spacebar. As a small side note, it's also important to make sure that your game view has focus in Unity by clicking on it so that it knows to register inputs. Something to notice about the movement of the cube is that it only moves once whenever the spacebar is pressed down. This is because our cube is only set to run when the spacebar is initially pressed down. If we want to change this, we can simply change our getKeyDown to getKey, so that the if statement runs as long as the key is pressed. However, if we want to do it this way, we also need to make a change to our vector 3 math. The reason for this is because since this code is in the update function, it is getting called every frame. Multiple frames happen within any given second, and if we assume that a computer runs 60 frames per second, then that means our cube will be moved 1 unit on the x-axis 60 times every second, which is way too fast. To fix this, we simply need to multiply the vector we are adding to our cube's position by time.deltaTime. What time.deltaTime is how long the last frame took to complete in seconds. So if we multiply our vector 3 by this number, all of our vector 3 variables will be divided to effectively achieve the result of moving our cube 1 unit on the x-axis every second. So now we officially have our cube moving. However, while moving it this way can be useful, it's also a bit of a hassle to write out entirely new vectors whenever we want to update our cube's position. Also, moving the cube in this way limits us to only moving it in global space, which can be annoying and mean that we have to write way more code than we need to. So let's change our current code to make use of a new method of movement that uses relative directions and shorthand notation. Before we do that though, we need to go over the concepts of local and global space. Let's look at this Pac-Man for example. To keep things simple, this Pac-Man is only shown in 2D, but keep in mind that all of the following topics still apply in 3D, just with an extra dimension. So in Unity, certain vector values can be represented by shorthand notations. In the case of a vector 3, the shorthands are right, left, up, down, forward, and back. Given this, we can look at the space our Pac-Man is in to understand the difference between local and global space. Keep in mind that because our Pac-Man is only in 2D, there are no forward or back directions, since those require a z-axis. In this example, we can think of world space as the screen. So the left direction of the world would always be to the left-hand side of the screen, and the up direction towards the top of the screen, right towards the right, and bottom towards the bottom. The local space in this example, we can think of as the orientation of our Pac-Man. So in this case, Pac-Man is facing the right direction of local space, and in this case, the right direction of world space. However, if we want to turn Pac-Man to now look towards the top of the screen, the right direction of Pac-Man's local space would now shift to be facing the up direction of global space. So if we were to now move Pac-Man locally to the right, we'd see him move toward the top of the screen or in the up global direction. In this case, Pac-Man is our object, and local space always pertains to a particular object in its direction. So if we were to have multiple Pac-Mans, all of their local right directions could point toward different global directions at any given time. So why is this important or useful? Well, because sometimes we want objects to move in a particular manner in global or local space, and having shorthand for these directions can be very useful. For instance, we may always want Pac-Man to only ever move in the direction he is facing, or in other words, his local right. If we were to do this with our old method, we'd only have access to global space, and would have to manually calculate the values for the vector 3 to add to his position to ensure this always happens. Now with these new concepts, we can instead just tell Pac-Man to move to his local right, as that is the direction he is facing, and save ourselves a lot of time. Coming back to our cube example, let's actually implement this. This is actually pretty straightforward, as all we need to do is change our code from using a custom vector 3 to using a shorthand notation. We want to move our cube on the x-axis. So in our case, we can either tell the cube to do so through local space or global space. Lucky for us, our cube is already oriented correctly with global space, so right in the cube's local space is also right in world space. We could implement this either way, but I'm going to make our cube move using local space. If we wanted to move the cube right in global space, we would just change our custom vector 3 to instead just be vector3.right. But since we are going to move our cube using local space, what we would write is this.gameObject.transform.right. As an added note, if we wanted our cube to move faster than just 1 unit every second, we could multiply this direction value by some speed value. We could also divide the direction by some speed value to make it slower. In this case, let's multiply it by 2 to make it go twice as fast. So now if we go back to our game and press play, then press spacebar, we'll see our cube now moves like it did before, but faster, and using our new code. And that pretty much covers the basics of how to use translation in Unity. The only thing left to do is to add more inputs and more directions. So now that we have an understanding of the basics of moving around objects in Unity using translation, let's apply that knowledge to learn how to use Unity's physics system to move things around. The first step when you want to make any object use physics interactions in Unity is to add a rigid body component to the object. To do this with our cube, we can simply click on the Add Component button, type in rigid body, and select the component from the list below. Once we add the rigid body component to our cube, we'll notice that it comes with a variety of different variables that we can configure. These different variables all affect the way that our cube will interact with the physics environment in Unity. Now I'm not going to go over all the different details about the physics system in Unity in this video, because it can get rather complex. So instead I'll focus on just the information we'll need to get our cube to move using physics. To do this, all we need to know is that the mass variable affects how much force is needed to move an object, the use gravity toggle affects whether or not the object is affected by gravity, which in our case we'll want to shut off or else, and the is kinematic toggle controls whether or not the object is affected by forces. We will want our cube to leave that checked off so that it can be affected by forces so that we can move it around. Alright, so now that we've got a rigid body set up on our cube, let's hop back into the code to set up moving the cube around using physics. To do this, we'll need access to our cube's new rigid body component. We could access this directly, but it'd probably be easier to set this as a variable and just access it that way. We could do this by declaring a public global variable and either dragging and dropping our rigid body component into the new variable location in the inspector, or by assigning the variable to the rigid body component in the start function. Either way, once we have access to the rigid body component of the cube, we can now use it to make the cube move. We can actually reuse a lot of our old translation code for this. However, instead of changing the cube's position directly, we want to apply a force to the cube's rigid body in its right direction. To do this, we would need to swap out the part of our code that sets the position of our cube, and instead add in our new rigid body variable, followed by the .addForce method. We would then place our movement direction and speed multiplier inside the function, and there are a lot of different ways to add force to a rigid body in Unity, and a lot of different force modes that we could use. But for this video, I'm just going to stick with add force as it is the main method of movement, and a force mode of force to keep things simple. Also, the reason we no longer need to multiply our vector3 direction by time.delta time is because forces are much less powerful than manually translating the cube every frame. So now that we have this new code, if we go back to our editor and press play, then press spacebar, we'll see that our cube slowly begins to accelerate and then picks up speed over time. Something else to keep in mind is that the cube will keep moving even after we have let go of the spacebar. This is because it maintains its velocity and will continue to move in a direction until acted upon by another force or by colliding with another object. And that's pretty much how to make things move using physics in Unity. Like I mentioned, there's a lot more to the physics system in Unity than I got into here, so I'm probably going to make a video on it going into more detail later. Also, one final really important caveat is that physics and translation don't play well together, and you typically have to decide on a main method of movement for an object beforehand and keep them separate. It is possible to make the two cooperate, but it requires some custom code to do, and you never want to have an object with a rigid body having forces be applied to it, while also having its position be manually translated at the same time, or things could get weird. But other than that, that should be all you need to know in order to get started making things move in Unity. I hope you have as much fun as I did the first time I figured out how to get movement to work and start messing around in Unity. I'm planning on doing more videos like this in the future, as well as some devlogs on an AI evolution simulator I've been working on, as well as a game that I'm working on. Feel free to suggest more video ideas that you might like to see in the comments, and subscribe if you want to stick around to see my channel grow. But regardless, thanks for watching.